All right. Good morning, good afternoon, good evening, everyone. Um, as we have listeners really coming from all around the world today, welcome to this first of 5 webinar series on color theory. Today we have our senior color scientist, Bill Binder, with us to discuss color and appearance. So I am going to pass it over to Bill and let him share with you his presentation. So just give me 1 second. I think I need to make Bill you the presenter. Go. All right, Bill, I'll let you take it away.
Okay, thank you. Hello, everybody, and welcome to today's webinar. I want to thank you for taking the time to be with us today. My name is Bill Binder, and I'm a senior fellow here at Datacolor. I'm part of the research and development group where my primary responsibility is to provide technical support and mentoring to my colleagues. I have over 40 years of experience working in the computer color control industry, where I was part of the teams that produced many of the color quality control and color formulation products available today. During that time, I've had the pleasure to work with many people, both colleagues and customers, who have been industry leaders and pioneers in the color technology field. I hope that this series of webinars will provide you with relevant color information that will be helpful in your job and career. Okay, we're going to get started. I'd like to start with a simple but accurate definition of the question, what is color? This is not a simple, there's not a simple answer to this question, but simply stated, color is perception, and this color perception happens in the brain. A one-sentence description could be, color is a perception by an observer of light which has been modified by an object. There are always 3 ingredients or elements in the object observing situation, and we can say that color perception depends on these 3 things: a light source, the object, and the observer. This is sometimes referred to as the color triplet. We will consider each of them and how they are part of the color perception process, beginning with the light source. The English mathematician and astronomer Isaac Newton was the first person to discover the fact that light is the source of color in the objects around us. Prior to Newton's discovery, color was thought to be the property of the object itself. Newton's experiment with passing a beam of white light through a glass prism proved that white sunlight consists of a mixture of colors. Newton coined the word spectrum for these colors. He then did a follow-up experiment where he recombined the colors with a second prism, again producing white light. So what is light? Light is a special narrow range of electromagnetic radiation. Electromagnetic radiation is basically a transfer of energy through space or a medium using both electric and magnetic waves. The electric wave and magnetic wave are perpendicular and in phase to each other and perpendicular to the line of travel. The electromagnetic spectrum spans a broad range from electric power waves and radio waves to gamma and cosmic rays. When you tune your radio, watch TV, send a text message, or pop popcorn in a microwave oven, you are using electromagnetic radiation. The human eye can only detect a small portion of this spectrum, which we call visible light. The horizontal distance between 2 consecutive troughs in the wave is called the wavelength, and the number of wavelengths that pass a given point every time is called the frequency. Wavelength and frequency are inversely proportional. That is, the shorter the wavelength, the higher the frequency, and vice versa. All electromagnetic radiation, regardless of wavelength or frequency, travels at the speed of light. For visible light, the wavelength range is generally from 400 nanometers to 700 nanometers. Now, a nanometer is 1/billionth of a meter. To give you some perspective, the wavelength of a cosmic ray over at the far end of the spectrum is 100,000ths of a nanometer, which would be 1 × 10⁻14 meters. with a frequency of around 300 times 10 to the 22nd. So these are high energy, high frequency, and very tiny wavelength. At the other end of the spectrum, electric power waves have an average wavelength of almost 5,000 kilometers. And the frequency of these waves is 60 hertz or 60 cycles, which is our common electrical signals. Newton chose 7 colors to describe the spectrum: red, orange, yellow, green, blue, indigo, and violet. The effect of the prism is to bend shorter wavelengths, the violet, more than the longer wavelengths, the red, thereby separating them into distinct bands of color. The light changes speed as it moves from one medium to another, for example, from the air to the glass of the prism. The speed change causes the light to be refracted or bent. And the degree of bending depends on the light path of the incident beam makes to the surface and the ratio of the refractive index between the two media. The refractive index of glass varies with wavelength of color of the color. So in other words, each color is bent differently, and this is known as dispersion. This causes the light of different colors to be refracted differently and leave the prism at different angles, creating the color spectrum. The variation of refractive index with wavelength is also the source of chromatic aberration in lenses. Okay, so let's take a look at start taking a look at light sources. Light sources may be precisely characterized by giving the energy or power of the light source at each wavelength in the visible spectrum. The resulting spectral power distribution contains all the basic physical data about the light and serves as a starting point for a quantitative analysis of color. The SPD, or spectral power distribution graph, is a true fingerprint of a light source and shows the radiant energy emitted at each wavelength in the visible spectrum. And as you can see here in this example here, this is a daylight type illumination. It's fairly has the same wavelength range across. A little more blue light. We see a little more blue light is being emitted here, but it's a fairly even distribution. Okay, the next slide here, we have a spectral power distribution for a incandescent or a tungsten light bulb. This distribution, you can see, is much different. It has a lot more red energy being emitted and green and less blue. Okay, the next one here is we're showing a fluorescent lamp. Now, a fluorescent lamp has a glass tube that's filled with a mixture of mercury vapor and other gases. When an electric current is applied to the electrodes, the gas inside is ionized and emits ultraviolet radiation. The inside of the glass tube is coated with phosphors that absorb the ultraviolet radiation and fluoresce or re-radiate the energy as visible light. So the spectrum of light emitted from a fluorescent lamp is a combination of light directly emitted by the mercury vapor, and you see these peaks here. These 4 peaks are the light from the mercury vapor itself, and this continuous part here, this is the light emitted from the phosphorus coating from the UV light that's fluorescing. So the spectral lines from the mercury emission and the phosphorescence effect give a combined spectral distribution of light that is different from those produced by the incandescent sources. Here we have an LED source, and in this case we have the LED is comprised of 3 LEDs in this example, where we have one at 440, 560, and 635 nanometers. And the final light is produced by what's called the white phosphor method, and it combines takes the short LED, a short wavelength LED here, and the blue photons that are generated from here travel through a phosphor layer, similar to how a fluorescent light that I explained earlier. But through that conversion, they're converted into yellow photons in this phosphor layer, and then the combination of that blue and yellow generates this whiter light. And you can see here that down here we can show how that is put together, that the phosphor coating brings the yellow and the red LED together, and it also brings up the peak, so that this is the final representation of the LED light. Now this has this peak. Visually, this will look like a daylight, more of a white light source, but it does have this strange spectral characteristic. Okay, here I'm just doing a comparison. I'm showing the three of the lights together so that you can get an impression of how much different they are from each other. Okay, now I was using the term source and luminant. And one thing, when we describe light sources, we must make an important distinction regarding the terminology we use. The term light source and luminant mean different things in the study of color. We use the term light source to refer to a real or physical source. For example, a specific incandescent light bulb is considered a source. And the luminant refers to a light that is defined by a set of numbers that represent the spectral energy distribution of a real source. This illuminant data may or may not represent the exact physical light source in question. For example, the illuminant A data provided by the CIE represents the average distribution of an incandescent light. It can be used, provide a standardized reference for everyone to use to perform colorimetric calculations. Now, I mentioned the term CIE here. Let me just tell you what the CIE means. The CIE is the International Commission on Illumination. CIE is the abbreviation for the French name Commission Internationale de l'Éclairage. They are an organization devoted to worldwide cooperation and the exchange of information on all matters relating to the science of color, vision, and lighting and image technology. Most light sources, and especially daylight sources, have a great deal of variation depending on the specific conditions of the atmosphere or geographic location. Here we see 6 different types of daylight sources. This type of variation would not be very helpful if we wanted to use natural light or natural daylight to do any kind of color evaluation. Because of this type of variation, color evaluations are usually made in light booths or under controlled conditions. Now here I'm showing 3 daylight illuminants, and again, since I'm using the term illuminant, these are representations from the CIE of average daylight. When performing color calculations requiring illuminant data, we can use one of these standardized illuminants to improve color agreement between different locations. And in case here, you can see that there's a D65. We have a D65 is the red here, and the blue is a D75 and the D50. You can see that the D50 is a more even distribution across the spectrum, and this is used a lot in the printing industry. D65 is very common and is probably the most common daylight illuminant used, and D75 is used for other purposes. I've used the term D65, D6500. So what does that really mean? Well, let's get into color temperature. Color temperature describes the color of light of a light source by comparing it to the color of a black body radiator at a given temperature. Now, a black body is a material that will absorb all light falling on it, and any radiation coming from it will depend on the actual temperature. As the actual temperature of the black body is raised, it radiates energy in the visible range, first red, changing to orange, white, and finally bluish white. Rather than delve into the physics of black bodies, which gets into quantum mechanics, it's easier to understand the concepts by thinking of the black body as a black material like a fireplace poker or a chunk of carbon that will be heated in a furnace. The poker at room temperature is black since most of the incident light is being absorbed. As we begin to heat the poker, it begins to glow. First, it'll come to a temperature of around 800 Kelvin, and we're using the Kelvin temperature. Hold on a minute here. We're using the Kelvin temperature instead of centigrade. And I have a little problem here with my computer for a minute here. Let me just hang on for a second. Okay, we're using the Kelvin temperature, which is the same as the centigrade scale. It's just that the 0 point is absolute zero, so it's 273 degrees different. As this black body is heated, it's going to start changing color. In other words, the appearance will change from red to orange to like a yellow, and as it's going up in visual change, the actual temperature of the black body is increasing. Now, if the color appearance of an incandescent lamp is like a black body radiator heated to around 2800 degrees Kelvin, we can say that the incandescent lamp has a color temperature of 2800 Kelvin. If the appearance of the fluorescent light is like a black body heated to around 5500 Kelvin, we can say that the fluorescent light has a color temperature of 5500 Kelvin. It's important to understand that the color temperature is not the physical temperature of the light source. It corresponds to the physical temperature of the black body radiator, where the color appearance is the same as the light that we're in question. Now, when we talk about this with lights, we usually term correlated color temperature. And correlated color temperature is a way to describe the light appearance provided by a light source. And it ranges in degrees of Kelvin from about 1000 up to around 10,000. A light source's color temperature lets us know what the look and feel of the light produced will be. The color temperature of a light bulb is assigned using the basis of correlated color temperature, which again is the color of a corresponding black body. Color temperature is meaningful only for light sources that correspond somewhat closely to the radiation of a black body. For example, a light that will go through the range from red to yellow to bluish white. It would not make sense to speak of the color temperature of, for example, a green or a purple light. Color temperatures over 500 K are called cool colors, while color temperatures in the range from around 2700 to 3000 are called warm colors. Now, warm really refers to the radiated heat of traditional incandescent lighting rather than the temperature. The fact that warm lighting in this sense actually has a cooler temperature often leads to confusion. Warm colors, including hues such as red, yellow, and orange, are colors we associate with fire and therefore warmth. Cool colors, bluish, are associated with cold, like the lighting we would get outside on a cold winter day with a blue north sky. Warm and cold in this context have nothing to do with the color temperature. It's important to understand that color temperature is not a measure of the physical temperature of the light source. Color temperature depends on the physical temperature of the black body radiator, whose color appearance is the same as the source being referenced. So like when you see that it's a warmer light, and the color temperature is actually lower, that's the confusing part. But generally, when you look at this range, whenever someone tells you that they have a light of a certain color temperature, when someone says, I have a 700K light, you'll know right away that it's a bluish, or what we call a cool type color. And that's really what all the lighting, whenever you go out and look at lighting or buy anything for a light, the color temperature will tell you what's the appearance of that light. Okay, just in summary then, the key point to remember here for all these light sources is that they have a different and many times unbalanced output of radiant energy. For both visual appraisal and colorimetric calculations, it's very important to know the light source or the illuminant characteristics. Okay. Okay, next, we're going to, we've talked about light and light sources. As we begin our discussion of the second part of the color triplet, the object, we can make an important point that color is not a property of objects. Objects only modify the incident light. In the case of the apple shown here, the incident sunlight contains all the wavelengths. The apple is only reflecting back the red and orange wavelengths. The green, blue, violet, and indigo wavelengths are not reflected from the apple. These wavelengths are being absorbed by the apple. Absorption is a process that converts the light energy to another form. In this case, the absorbed energy is converted into heat energy. The absorbed radiation is re-emitted as infrared energy at a higher wavelength outside of the visible spectrum. So we don't really see the infrared or heat energy, but it is converted and it's not available for us to see. We perceive the color of the apple as red because the red light is reflected from the apple. The apple is red only as long as the light source has red energy. If the apple were illuminated with a light source that had only blue and green light, the apple would not look the same. In this case, the blue and green light would be absorbed and there would not be any red light to reflect back. The apple would look dark brown or black. Okay, we quantify the object's reflectance property by using the spectral reflectance curve. The spectral reflectance curve, or %R curve, shows the amount of light reflected at each wavelength. In this example, we can see that the apple is absorbing light in the blue and green region from around 400 to 600 nanometers and reflecting back orange and red light from around 600 to 700 nanometers. Just as the spectral power distribution curve is the color fingerprint for a light source, the %R curve is the color fingerprint of the sample, in this case the apple. The %R data is obtained from an instrument called a spectrophotometer. Okay, here's just giving you some more spectral curves. Here's a spectral curve of a cyan blue color. In this example, we can see that the sample is absorbing light in the red and the green region and reflecting back blue light from around 400 to 560 nanometers. Okay, here we have a %R curve for a green color. In this example, we can see that the sample is absorbing light in the red region and also over here in the violet, and it's reflecting back in the green from around 400 to about 540. Okay, here I have a number of spectral curves. We have here a yellow, and the yellow is absorbing blue energy or violet energy, and it's reflecting back red and green. And the combination of red and green additively to our eyes, we perceive yellow. Over here, there's a violet or a purple, and you can see in this one that we're reflecting back violet light and some red light, but we're absorbing green. Here's another red, again absorbing blue and green energy and reflecting back red. And here's a gray, and in the gray sample, we're reflecting back light evenly across the spectrum. So this gray, different shades of gray would have this even distribution, as long as they're made with a pigment that is of this character. Okay, here's an example. This is sort of like a real-world example on spectral curves. I have here a blue pigment and a yellow pigment at a certain concentration, and these are the spectral curves of those. Here's the blue, and here's the yellow. If we mix these two together, in other words, if I take them and make a mixture and make a paint from them, what we're going to produce is another color. And I'm sure all of you know that, of course, when we mix yellow and blue together, we're going to create green. So here's the result. After I mixed these together, I made another sample up and measured it. And you can see that this green curve here, this with the dotted line, with the dots on here, that's the actual spectral curve of the mixture. And you can see how it follows the curves in this where I started with the yellow, that the green that was made here were at the same concentration as these were over here. And you can see that how that produced the green curve, so that the blue pigment is absorbing, over here it's absorbing red light, and the yellow is absorbing the violet light over here in blue, and the only light that's left to come back to the eye is the green radiation. And one thing with the spectral curve is you can see, like for example, there's a little bump here at around 680, 660. That's indicative of the pigment phthalo blue, and we can pick that up on the spectral curve. And if by just looking at the spectral curves, a lot of times you could just figure out what kind of pigments that you might want to use for a color match. Now, we don't have to do that generally anymore because we use color matching software and systems that do this efficiently. But that's kind of, sort of how even systems work. You look at the spectral characteristics of all your materials and you try and match a target material. Okay, Let's take a closer look at object and light interactions. Generally, we can define two main light and object modes, reflection and transmission. And looking at these in more detail, we can state that light in either mode can be either absorbed, scattered, or refracted. So basically, these are two modes of vision. Light is reflected off, and we see light in the reflective mode, or light can be transmitted through objects, and we see it in the transmission mode. Now, what happens is, I mentioned the term absorption and scattering. Absorption, again, is light energy is removed, converted to heat. And scattering is just light energy is changed in direction. It can still continue to go through a material. But both absorption and scattering are very important in the way objects look. So we normally distinguish materials by the ability of light penetration. So we say these are the three modes. We say something is transparent, where light can be absorbed, but generally is transmitted without scattering. Light easily penetrates the material. A sample can be translucent, where light can be absorbed and scattered, but can penetrate the material. So the translucent is we can still see through it. It might be cloudy because of some scattering, but we call that a translucent sample. Or a sample can be opaque, where light can be absorbed and scattered, but cannot penetrate the material. So the opaque object would hide anything behind it. If you're painting a wall, you want something opaque, so you want to cover. You don't want to see what's in the background. Okay. Also, when we talk about object and light interactions, there's a surface effects. A portion of the light energy is reflected off the surface of an object. This is called specular reflection. It is due to the difference in the refractive index of the material and the air. The type of surface, smooth versus rough, determines how the light is reflected. It can be diffuse from a matte surface or very directional from a glossy surface. Gloss is an important appearance characteristic in addition to color. So here you see when you have a very glossy surface, the light is directional and you can come right to the eye, but you can also look away from that and see a very nice deep color. However, when we have a matte surface and it has a diffuse reflection, no matter where you look, you'll see the surface, and the surface or the color will tend to look lighter or duller. Okay, let's talk about in general how objects modify light. And here we're going to take a look at the interior of a sample. When light first strikes the surface, a small portion of the light is reflected off the surface, and we call this specular reflection. And again, depending on the surface, whether it's smooth or it has a rough exterior, it'll either be diffuse specular reflection or regular. This amount is roughly around 4% of the light does not make it into the sample and is reflected off the surface. However, most of the light does get into the interior of the sample. And when light is inside the sample, again, different things can happen. And again, the main things are absorption. The light can be absorbed, converted to heat. This is a blue object. It's absorbing red radiation and green radiation and reflecting back the blue light. Light can be scattered. By scattered, the light hits a particle. It's just changed in direction. It's still available to keep bouncing around inside the sample. Light can be transmitted through the sample. Light can be refracted if it comes out of the sample again, or when it goes in, it's changing direction. Or what can happen inside the sample, you can have something called internal reflection. If the light hits the interface at a certain angle, all the light will be reflected off the surface, and it'll be available to be bounced around again inside the sample. So this is going on at all times inside the sample. If there is light available to exit from the sample, like the opposite side, the object would be considered translucent. If all the light is either absorbed or scattered in the object would be considered opaque. And in this case, we're just showing a sample where we have some blue pigment particles, probably in like a clear resin. Okay, let's move on. We're moving on now. We covered the object. Let's talk about the observer. Looking at the third part of the color triplet, we've discussed the light source and object, and now we're going on to the observer. The human observer in our discussion comprises both the human eye and brain. The eye is a data gathering structure, much like a camera, while the brain is where the perception of color is realized. Visual information is sent from the eye to the visual cortex along the optic nerve. The final processing of this visual signal is completed in the visual cortex and in other areas of the brain. Let's look at how the eye captures the visual information. Light enters the eye through the cornea in the front here, and the cornea bends the light rays so that it can freely pass through the pupil, which is the opening in the center of the iris. The iris works much like the shutter on a camera. It can enlarge and shrink depending on how much light is entering the eye. After passing through the iris, the light rays pass through the eye's lens. And the lens is a flexible structure and works much like the lens in the camera, shortening and lengthening in order to focus the light rays on the retina. Now, the retina receives the image that the cornea focuses through the eye's internal lens and transforms this image into electrical impulses that are carried to the optic nerve and the brain. Now, back here, I'm just showing in this example, we have the rods and the cones. So let's talk about them in a little more detail. The cone cells are responsible for the photopic or color vision, or color sensitivity. We have about 6 to 7 million cone cells in the retina of the human eye. They're typed as L, M, and S cones, and basically they have different photosensitivity. The L cones respond to light of long wavelengths, such as red, the M to the medium, such as green, and the S cones refer to light of short wavelengths, such as blue. Over here, we're showing you the actual sensitivity where we peak with the cones. You can see that the M and L are sort of fairly close together. We don't have a perfect distribution over here. Now, the rods are responsible for dark or scotopic vision, and they're 1,000 times more sensitive than the cones, and they're better at detecting rapid movement. There are about 120 million rods in the retina. They do not detect color and are predominantly found in the peripheral areas of the retina, not near the center. And over here in this chart here, this dashed line, that shows where the peak sensitivity is for the rods. Okay, get into a little bit of theory here on vision theory. The trichromatic theory, which is also called the Young-Helmholtz theory, is based on the idea that the visual system is mainly responsive to 3 colors, red, green, and blue, and that color vision is a result of the combination of the differential responses from these 3 components. Hermann von Helmholtz, he further developed the theory in 1850, and again, he just identified that these were indeed that we were responsive to red, green, and blue light. Now, based on a phenomenon of color after images, Ewald Hering proposed the opponent theory of color vision. He said that color vision takes place in 3 channels where opposite or complementary colors are in competition. He said the visual system is responsive for the 3 color pairs, which are green, red, blue, yellow, and black, white. His theory suggested that the colors in each pair oppose each other. For example, the red-green receptors cannot send messages about both colors at the same time. The theory explains the concept of after images. Red and green are complementary colors. When we stare at red for some time, our redness detectors kind of get tired, and their antagonists, which are the green receptors, take the lead, and we see a green after image. This is also part of where you never really have a greenish red color. A color is either red or green. It's never greenish red, or same thing with yellow and blue. Now, which theory is correct? Really, both theories are needed to explain the complexity of color. Though the chromatic and opponent theories were initially thought to be at odds, we now understand that the mechanism responsible for the opponent theory receives signals from the 3 types of cone process and just process at a different level. In addition to the cones, which detect light entering the eye, the foundation of the opponent theory involves 2 other types of cells, the bipolar and the ganglion cells. So in this picture here, you can see that we have our rods and cones here, and then after the rods, or after the cones, we go to what are called the bipolar cells and then these ganglion cells. This is the area where we think this opponent theory comes into play. This is where the red, green, yellow, blue. So in this diagram here, I'm showing you that we start with the red, green from the cones with our normal trichromatic theory, but this additional processing that's done here before it gets to the visual cortex is where we think that the opponent theory comes into play. Just to say one thing, this is a very complex process, and we still don't completely understand exactly how we finally see color. Okay, let's take a look at, I mentioned the after image. I'd like you to take a look at the dot here, and what you want to do is just stare at that dot for a while and just keep staring at it, because in a little while I'm going to just change this to a blank field. And what I want you to do is just keep staring at that dot, and I'm going to see if we can show you what the after image is like. So is everybody staring at the dot? You're all staring at the dot. Okay, hard stare. Okay, now after I switched it to the white field, hopefully you saw some type of an after image. Your eyes were being saturated by those colors, and the minute I hit the white screen, you should have seen the opposite of those colors. So here's what you should have seen. In other words, the original picture on the left is what you were staring at, and the after image would be something like on the right. So where you were staring at green, the after image was red. Yellow, the after image was blue. And again, when you were staring at blue, the after image was yellow, and exactly the opposite. This can't be explained with just the trichromatic theory of red, green, and blue receptors. This is where Heron's opponent theory comes into play, and it can be explained. Okay, moving right along here, we have, I like to finish the session here by discussing color mixing. This is a topic that causes some confusion when first encountered. There's really two main types of color mixing: additive color mixing and subtractive color mixing. Additive, shown here on the left, is mixing what happens when lights of different wavelengths are mixed. When we add all the different wavelengths of sunlight, we see white light rather than many individual colors. It's called additive because all the wavelengths still reach our eyes. We're adding together. So it is the combination of different wavelengths that creates the variety of colors. Now, this is the process by which color is produced on television or on your computer monitor. You have pixels that are joining each other, for example, and there's a red, green, and blue pixel. And if you want to see yellow, the red pixel is lit and the green pixel is lit. In the combination, you see yellow. If you want to see just red, only the red. But this combination, this additive mixture, has to do with mixtures of lights. So when you're talking about monitors, TVs, you're in this additive world. Subtractive color is creating a new color by the removal of pigment, of wavelengths from light. Subtractive color mixing occurs when we mix together paints, dyes, or pigments. When we mix paints, both paints still absorb all the wavelengths that they previously did, so that we are left only with the wavelengths that both paints reflect. It's called subtractive mixing because when paints mix, wavelengths are removed from what we see. So for example, over here, the subtractive primaries are called cyan, magenta, and yellow. So and this is again how when you printing or photograph pictures are all done with the subtractive method. So if we mix together cyan and magenta, we're going to produce green. So again, the cyan is going to remove red light, the yellow is going to remove blue light, and we're going to be left with green light. So in other words, we're subtracting out a portion of the spectrum. If we mix all three together, we get black because we're taking out all the primary colors. Additive color mixing basically happens when we mix lights of different colors, whereas subtractive color mixing occurs when we mix pigments of different materials. Okay. Okay, some final comments here. We started the webinar by giving this definition of color. That color is perception by an observer of light, which has been modified by an object. The understanding of how the light source, object, and observer relate to each other will be an important part of your color technology training and will be a key element of color communication between you and your customers. I hope that this webinar has provided some useful information. In our next webinar, we will see how we can take this concept of light, object, and observer as a color perception and build a colorimetric or numerical specification from it. So the next seminar, we're going to talk about the CIE standard observer, where we're going to take the human observer function and come up with a method that we can put numbers on this. Talk about tristimulus values, talk about metamerism, color order systems, etc. So with that, I'll end the session, and I thank you very much for listening.
Yeah, Bill, great session. We do have actually quite a few questions that came in as well. So I know we ran a little bit over time, but if everyone still have a few minutes to hang on. So first question came from Ralph. He's asking something around the light source. Is there any significance to the D50, D65, and D75 intersecting at 560 nanometer? Pretty scientific question.
Could you repeat that question again?
Sure. He's asking if there's any kind of significance to the fact that both the D50, D65, and D75 are all intersecting at 560 nanometer.
Just off the top, no, not really. I think it's just that that's where, because each of them has more, basically that will have more blue light and red. The blue and the red light is the differencing, and that's sort of almost where they're just coming together. Since they're illuminants, these are trying to be a capture of what this average daylight would actually be. So no, I wouldn't have any significance, or I don't know any significance to that.
Okay. The next one, maybe it's not necessarily a question, maybe more a statement, asking crazy question. If daylight has broadest spectrum, why don't we as an industry review under D65?
Well, I think a lot of times D65 is commonly used, but again, it depends on where the products are going to be viewed and things like that. So and again, we'll get into the next webinars. You really have to have multiple illuminants because of the problems like metamerism. When we get into situations where if the spectral curves are not alike, the sample will not match under all light sources. And again, for visual appraisal, a lot of times you want to make sure you're viewing under the same type of lights that maybe your customer is going to be viewing and things like that. So I think there's a lot of things that go into the decision of exactly what to use, and again, a lot of it has come from years of experience of people doing things, but generally, especially when you do things with numerically, you can use a lot of different illuminants and get a lot of different information. So I hope that answers it. I'm not sure if that answered the question, but
great, thanks, Bill. Next question. What if an object absorbs all radiation and doesn't reflect anything? Does that mean the object literally disappears to the human eye?
Well, it becomes black. In other words, if an object absorbs all radiation, it would be, for example, a black object sort of does that. It absorbs radiation, and that's why you view it as being black. So I think that's the answer to your question. But yeah, okay. It does. It doesn't disappear in a sense that we still see specular. We still see the object. It's just that the amount of radiation that's coming back to the eye has been drastically reduced. So,
right.
I'm not sure if that was the answer. It doesn't actually disappear, but it does lose color, become black.
Right. Okay, great. I'm conscious of time. We have actually a lot of questions coming, which is great. What we'll do is probably not going to be able to get to all the questions on this webinar right now. We will address all your questions probably individually after the session via email. So be assured, we actually have tons of questions right now come flying in, so that's great. And we will also provide a PDF version of the presentation to the attendees as well. So look out for that. All right, so with that, I think maybe we can close this webinar because I know we are running out of time. I think Bill, do you have a
Yeah.
next slide? I just
Yeah.
want to, yep.
Yeah, I just want to say something.
Oh, go ahead.
Like I said, any questions? I mean, are we'll definitely try and take a look because it helps determine what's important or what people really want to understand. So the questions are great for us to do further, future webinars, and we can possibly incorporate some of them into them. So.
Yeah,
Okay.
exactly. Also, after you leave the webinar, there will be a couple of simple questions to survey to see what topics you'll be interested to learn more. Please be sure to answer those survey questions. And lastly, I just want to mention we do offer classroom-style lectures as well as hands-on learning. When things eventually return to normal, you can visit datacolor.com, our website, under the Academy area to look for a schedule of in-classroom trainings. Under the Data Color Academy area, we also have our blog where you can read more about industry trends, color science informations, user tips and tools, and etc. So please follow our blog for more useful information. And I'd like to thank Bill for your great presentation, and thanks everyone for attending and listening to this webinar. And I hope everyone join us next week at the same time for part 2 of this series. Thank you, everyone. Have a good day, good evening, good afternoon.
Goodbye, everybody.
Bye.